Okay, assalamu alaikum. Welcome to the third set of the tutorial videos, and this time we're doing, let me get that close here, we're doing worksheet number 3, which basically covers the potential, electric potential, and also the potential energy, electric potential energy, and also some of the associated problems with it, especially the work energy theorem. Okay, let's start with the first question. And the first question, it says that you have we have 6 charges are placed on this geometry, which looks like a rectangle of sides A and 2A. And the question is asking you to calculate with V is 0 at infinity, calculate the potential at the center of the rectangle. So he wants the potential at this point here, at the center. Now, what I would advise you to do is to split the problem into 2 parts. First, find the potential due to the points at the corner, and I'll tell you why I do that. And then find the potential due to these points, and then add these up. So let's call V1 or Vi will be simply potential due to charges at the corner. So Q's at the corners, right? And V double I is the is the potential due to the other charges. Potential due to other charges, or due to this one and this one, due to side, let's just call them side charges. Okay, so the reason I'm doing that, because I see there are something that I can do with these ones, because the distance from the center to each one of these points is the same. So that means it's easier for me to add algebraically. So the first thing that I need to do is to find what is this distance here, okay, which is the same for all of these charges. And as you can see, it will be A over 2, and this side is A. So R, let me call it R, which is the same for all these 4 charges. It will be simply the square root of A squared plus A over 2 squared. Okay, so it will be A square root of 1 plus quarter. Okay, so that's what the area should be, and that's what you do. You should calculate what that is equal to. So once I do that, then the potential due to the charges at the corner, let me call it V1 or Vi, is equal to, of course, K 1 over 4 pi epsilon, and then this is 2Q1 divided by R, which is this guy, right? Plus minus Q1 divided by, again, the same distance, plus 2Q1 divided by the same distance, plus minus 3Q1 divided by the same distance. So as you can see, all of this comes out, and this will become 1 over 4 pi epsilon R, which is A multiplied by 1 plus quarter, and then multiplied by 2Q1 minus Q1. So this 4Q1 minus 4Q1 is equal to 0. And that's why I suggested that. So the V due to these charges, the corners, is really equal to 0. Right? So the only thing that you need to do, you need to find V due to these 2 charges, which is straightforward, can be done very straightforward. So that means V, let me call it V2, let me just make sure, yeah, V2 or V double I is 1 over 4 pi epsilon, and remember the distance here from there to there is A over 2. So it's 4Q2 divided by A over 2 plus 4Q2 divided by A over 2, and that you can solve. Remember the distance A is equal to 0.39 meter or 39 centimeters, and you can do that straightforward. And that's it. That's the solution to the problem number 1. Okay, so he wants the infinity. So yeah, he's assuming that V is equal to 0 at infinity, which is something that we worked out several times in class. Okay. The second question, that's a little bit, you need to do a little bit of calculus. So he's asking you, you have a positively and a negatively charged rod, and he wants you to find the potential at this point due to that. Okay. We've done this in class, to be honest with you, and we do not really I do not really have to go over it, but let me just very quickly tell you what you should do. And the difference between the minus and the sign is simply in here, in dq, that's all, because dq is equal to, or dq is going to be lambda times L at the end. When you integrate over q will be lambda times L, or minus lambda times L for this guy. So q here, the total charge will be minus lambda times L, because this is L over 2, L over 2. And here, q, the total q will be L times lambda. So the only difference is going to be in the negative and the negative sign and the charge over there. So using this definition for the potential, V is equal to 1 over 4 pi epsilon dq over r. Now, the only thing that you do not know is this r here. Okay, what is this r? R is simply, because remember, dq is this guy here. dq is this small infinitesimal point. And so this is dq. And r, so this distance r will be simply the square root of x squared plus d squared. That's what the r is equal to. So when I substitute it here, so it will be, V will be equal to 1 over 4 pi epsilon naught, and then dq over this distance here, x squared plus d squared. The only thing that I need to know is dq. What is dq? dq is defined from here. If I take lambda to be x, lambda to be constant and x and L is x, so dq will be lambda dx. And x goes from minus L over 2 to L over 2. Okay, so this will be equal to dx, lambda dx over the square root of x squared plus d squared. So the integration that I have to do is the following: is v, of course, is equal lambda over 4 pi epsilon, and then I have to integrate dx over the square root of x squared plus d squared, which we discussed that in class, but let me just remind you of what that integral is equal to. It's right here. This integral, in fact, is equal to ln, so this integral here is equal to ln x plus the square root of x squared plus d squared, and of course you have the limit from minus L over 2 to L over 2. Okay, or you can take it from 0 to L over 2 and multiply by 2, it depends there. So minus L over 2 to L over 2, that's what he divided the minus L over 2 to L over 2, and then you can evaluate that. Okay, so let me just make sure that everything is within the screen. Okay, that's it. So you just need to do a little bit of calculus to calculate this integral, and then multiply it by lambda over 4 pi epsilon. And for the other one, for the negative one, the only difference is going to be is in lambda here, it's going to be minus. That's the only difference you're going to have. So the potential will be negative. That is taking potential at infinity to be equal to 0. Okay. All right. The second question, which is this guy here. Okay. So what does he want here? You have charges which are placed. Let me just take a different color here. These charges which are placed at these positions, and where this is L, this distance is L, and this distance is also L. So this is basically a square. And what does he want? He wants, first of all, a square of side L is equal to how much work do you need to bring a particle that is equal to plus 6e initially at rest from infinity or infinite distance to the center of this sphere. So you need to here, this point here. You need to find the work, and work is equal to Q delta V. Okay. Now remember, you're taking it from infinity, so that's your initial point, to the final point, which is so it'll be minus. But never mind the minus for now. What we need to do is to calculate delta V, right? Delta V, which is equal to V initially, V infinity, minus V center. Okay, so that's what you want to do, the V at the center, and this is V at the center point here. What I need to do to find V the center, of course, is equal to 1 over 4 pi epsilon, and I take each point, and this is exactly the same as I've done in question number 1. So this distance here will be the same as this distance, the same as this distance, same as this distance. And remember, this is L over 2, and this is L over 2. So the R, my R here, my R for these guys, my R will be equal to L over 2 squared plus L over 2 squared. Okay, and you have to do that. So it's basically L over 2 square root of 2. Okay, so you take the L square and L square, you take it out, and that's what your R is. And remember, the distance here is 0.4. Okay, 0.4 meters. So it's basically, let me write it here. So it's minus 3e divided by the distance, which is L over 2. I'm just going to write one of them, and the rest is going to be, and then minus e divided by r, same thing, and then plus 3e divided by r, and then plus e divided by r. Okay, so you see that you have these two cancel, these two cancel. Again, I get 0 for this one. The only thing that I need to do is the potential due to these two charges, which the distance is L over A. So let's call this is V corners, and V due to these guys is equal to, again, 1 over 4 pi epsilon, and then minus 2e divided by L over 2 plus 3e divided by L over 2. And then you see you have 1e, and you can calculate that knowing what the charge of the electron, which is, what E is equal to minus 1.6 times 10 to the minus 19 coulombs. Okay, so we've done that. So that's the now once you found that, that's delta V, because V final is V infinity is 0, and that's your V center is equal to this. Then you multiply it by Q. The charge is plus. So this Q here is really plus 6e. So you multiply it by 6e to find the work, which is equal to that. Okay, and that's it for the first or for this question. It's exactly the same thing. The only thing that you have to do the work, which you need to multiply by the charge, which is equal to 6q. Okay. Next question is straightforward, but you just need to understand a few things here. Now, what does he want? He gave you the radius r, which is equal to r is equal to 8.5 centimeter. Okay, which is 0.85 meter. Okay, and he gave you Q1 is equal to some value, Q2 pico coulomb, so you need to multiply it by 10 to the minus 12, and he gave you Q3. What is the net electric potential V at the center? So what does that mean? That means I have to do V is equal to this 4 pi epsilon dq over r. But remember, the distance r is fixed for all of them, right? For all of them is r. So I can do V net is equal to 1 over 4 pi epsilon, and then 1 over r, and then I have dq1 plus dq2 plus dq3. Each one of them will be integrated. But remember, this is simply r theta, and each one of them has specific. So I can, and he gave me the values for each one of them. So I don't have to even integrate because these are constants. So they simply come out. So 1 over 4 pi epsilon 1 over r dq q1 plus q2 plus q3, because he gave me the values of these. If he didn't give me the values of these, then I have to integrate over the angle and find lambda and find all that. But he gave me the value. Okay, and as I said, these are constants. So it's just, as I said, it's simply straightforward calculations. All right. So that's the solution to this problem. It's very straightforward. Just you need to be careful with some of the math. It's pure math. It's purely mathematical problem once you understand the little bit of physics it has. Okay. The last question in this segment, in segment number 1, is actually the question on page, question number 6 on page 5, which is this question here. So this question is saying that you have 2 points, 2-point charges, plus 2 microcoulombs and minus 6 microcoulombs. One of them is placed at minus x is equal to minus 1, and one of them is placed at x is equal to 2 centimeters. And he wants you to find a point at which the potential is equal to 0 in between them. So what does that mean? That means I have 0. Let me just change this. This is thin, a little bit thin. 0 is equal to 1 over 4 pi epsilon is and q1 divided by r1 plus q2 divided by r2, and r1 is this distance here, that's my r1, and r2 is this distance here, provided that this is my x point. Okay, so that means what? That means my equation becomes 1 over 4 pi epsilon q1 divided by x plus 1, because this is x and you have you. So the distance from here to there is x plus 1. And then q2 is equal to, this is, remember, this is x, and this is the distance I want. So it's x, right? This is x, and x minus this. So it's x minus point, or actually let me just keep it in centimeters, minus 2 centimeters. Okay? So this will go with the 0, and then this is minus. So they will, I have, if I take it to the other side, it will be 6 divided by x minus 2 is equal to, this is 2, so 2x plus 1. And then you can solve this by, maybe you can do this, 3. So this will give you 3x plus 1 is equal to x minus 2. So 3x plus 1 and 2, sorry, this is not x, it's 2 minus x. 2 minus x, right? Not x minus 2. Because remember, I'm looking for this distance here. This distance is simply, if this is x, then this distance here is 2 minus x. Okay, so this will be 2 minus x. If you do that, then I have 3x plus 3 is equal to 2 minus x. So that means what? That means if I take this to the other side, I have 4x is equal to minus 1. Right, 3 will go there minus. So x is equal to what? X is equal to minus 1/4. So that means it's somewhere here, 0.025. That's what. That's where you should place the charge. This charge here, or the sorry, not the charge, but this is the point at which v is equal to 0. So this is a point of 0v. Okay, and that's it. Okay. So let me just, I think this is not within the screen, so let me just put it this way. So in conclusion, this is the first, as I said, the first video, and the second segment, or the second video of this part, it will be on the questions that are taken from the textbook, and we'll do that in the second video. So good luck, and hopefully this will help you with your solutions.